All right, welcome to The Explainer. Today, we're going to dig into one of my favorite, most elegant shortcuts in all of calculus. It's a technique called differentiation under the integral sign. Now, this might sound a little strange, right? How can you make a problem more complicated, but somehow make it easier to solve? It feels like a total paradox. But in math, sometimes adding a new layer, introducing a little twist, lets you pull off a clever trick that sidesteps a really tough calculation. And today, we're going to learn that trick. At its heart, this whole technique is like a mathematical superpower. It's all about knowing exactly when and how you can just swap the order of two of the biggest operations in calculus, differentiation and integration. Okay, let's get into it. First up, we're going to start with the most basic version of this rule. This is the one you use when the boundaries of your problem, what we call the limits of integration, are just fixed numbers. So, what's the big idea here? Well, imagine you have to take the derivative of an integral that has fixed limits, from a to b. Normally, you'd have to solve the integral first, then take the derivative of the result. But this technique lets us do something amazing. You can just push that derivative inside the integral sign and differentiate the function in there first. It sounds simple, but this swap can turn an absolutely horrible calculation into something much cleaner. Theory is one thing, but let's actually see how this works with a real problem. Our goal is to solve this derivative. Now, sure, you could just muscle your way through this with the standard methods, but we're about to see how our new shortcut makes the whole process so much more elegant. Okay, so this is a tale of two paths to the exact same answer. On the left, you've got the hard way, the brute force method. You integrate first, which gives you this kind of clunky fraction. Then you have to break out the quotient rule to differentiate it. And nobody likes the quotient rule. It's messy. But now, look at the path on the right, the smart way. We use our shortcut. We differentiate the inside part first. That gives us a much friendlier function to deal with. Then all that's left is to integrate that simpler result. And here's the magic. Both methods get you to the exact same, pretty complicated-looking answer. But the journey we took with our shortcut was just cleaner, more direct. We got to avoid that whole wrestling match with the quotient rule. This really proves it. The technique works, and it's a much more elegant way to get to the solution. So that works great for fixed limits. But what happens when the limits themselves are moving? What if they're functions of our variable? Well, for that, we need an upgrade. We need a more powerful tool. And that brings us to our second section, Leibniz's rule. Think about it like this. What if the goalposts of our integral aren't stationary anymore? What if they're also changing right along with our variable? That simple rule we just learned isn't going to cut it. We need a way to account for that movement at the boundaries. So how do we build this beefier rule? It's actually pretty logical. We start with the core idea we already know, right? Swapping the derivative and the integral. That's step one. But since our limits are moving, we need to add correction terms. So, step two, we add a term that accounts for the changing upper boundary. And for step three, we do the same thing for the lower boundary. It's just our original shortcut plus two new pieces. And here it is in all its glory. This complete formula is Leibniz's rule. It combines our original trick with those two extra terms to handle the moving limits. This is the full power tool, ready for pretty much any situation you can throw at it. So we've got this awesome new tool. What's it actually good for? Well, let's put it to the test on a really important function, one that shows up all over statistics and physics, the error function. This right here is the famous error function, or ERF of z. It's super important for things like probability theory, but here's the crazy part. Look at how it's defined. The function is an integral, and not just any integral. It's the integral of e to the minus t squared, a function that's famously, notoriously impossible to solve with basic calculus methods. So that's the big puzzle, right? If you can't even solve the integral in the first place, how on earth are you supposed to find its derivative? Well, this is the beautiful part. We don't have to solve the integral. We have Leibniz's rule. Let's just walk through our three-part rule. First, the core part, the integral of the derivative inside. But wait, the function in there, e to the minus t squared, it doesn't even have a z in it. So its derivative with respect to z is 0. The whole first term just vanishes. Okay, part 2, the lower limit. The lower limit is 0, a constant. It's not moving, so its correction term is also 0, gone. All that complexity, and we are only left with the final piece, the term for the upper limit, z. And when you evaluate that last piece, the result is just stunningly simple. The derivative of this super complicated error function is just the constant out front times the original function from inside the integral, with the t swapped out for a z. That's it. A big, scary 3-part rule just collapsed into this one beautiful, elegant expression. It's a perfect showcase of how the right tool makes the impossible seem easy. And this isn't just some mathematical party trick. The error function is a totally legit, well-behaved function. It has real properties. It equals 0 at 0, it goes to 1 at infinity, it's an odd function, and as we just found out, it has a surprisingly simple derivative. It's a fundamental piece of the mathematical universe. All right, so let's zoom out. What's the big picture here? What's the main thing you should walk away with from all this? We basically went on a journey. We started with a simple, clever trick, swapping a derivative and an integral. We then leveled that up into the much more powerful Leibniz's rule, so we could handle moving limits. And then we used that new tool to do something that seemed impossible, to easily find the derivative of the error function and get a beautifully clean result. And that really just leaves you with one final thought. It's a great reminder that so often the hardest problems in math and science aren't about just grinding harder. They're about finding a different angle, a new perspective, or that one clever trick that just makes everything click into place. It makes you wonder, doesn't it? What other impossible problems out there are just waiting for their own elegant shortcut? That's all for this explainer. Thanks for watching.